Hi, good afternoon. Good day, everyone. Welcome to this week linear regression with log transformation. So let's first look at this week 11.1. Okay, so log transformation. So first is when you apply a log transformation on a list of numbers, then there will be effect of squeezing the values for those values in the sample which has contained larger value, and there will be some effect of relatively stretching those sample values which is smaller in this list. Okay, so this is overall impact for log transformation. So you can have a look at this effect of a list of values for 1 to 100 when we apply a log. Then you are noticing that the values near the 199 and 98, the distance between that pair of values gets squeezed more compared with those values in 1, 2, 3, 4. Then when you apply the log, then relatively the level of squeezeness is lesser. So here is another example. Let's say if your data sample is from 1 to 11, your median will be 6. It will be staying in the 6 even after you apply these log x. After you apply the log x, the value you can see from the y-axis here, the 6 median will still be maintained at 6. When your value are all greater than 1, you will notice that actually each of the x value get squeezed. Okay, get squeezed. However, when you look at it on the right side, this example B, so the x value is from 0.1, 0.2, 0.3 up to 2, okay, with a step of 0.1. So we'll see that for the values smaller than 1.0, that each of the x, the relative distance actually gets stretched, okay? Then for those values greater than 1, then they get compressed. So a log transformation stretches value near 0 and below 1, though that's absolutely speaking. And compressed value is greater than 1. Okay, so that's the characteristic of applying log transformation. And next is, if you're noticing a distribution is right skewed, so you have reasonable ground to apply the log transformation. Okay, so log transformation. So one of the rule of thumb is if you find the skewness is greater than 1, that means it's right skewed, heavily right skewed. If it's greater than 0, it's right skewed. It's greater than 1, it's heavily, highly right skewed. Then it's reasonable to apply the log transformation for your dependent variable, for standard dependent variable. Okay. Yeah, we apply log transformation. So another thing is you need to note here before you will move here. So let's have a look at some of the demo that we show here. So week 11 R demo. Okay, so we're looking at this example A. The example A is here on the left side of the example. So we're creating a X variable that will display x-axis from 1 to 11. Then we can find the median is 6. Then y equal to log x. Then what is the transformed log x value? Then you can actually plot it. You are seeing that for the list of 1 to 11, then after you apply the log transformation, log x is this. Okay, so then we can also plot the relationship between x and y. So this is what you are seeing on the left side. Okay, left side. Then for example B, we're creating an x from 0.1 to 2 with a step of 0.1. Then the median is the average of 1.0 and 1, so it will be 1.05. So that's a median. Then y is the log x. Then you can also plot it. You're actually seeing this. This is log x. So for those values is lesser than 1, the x is lesser than 1, the actual distance get stretched, okay? For the values higher than 1, then they will get squeezed. And this is the plot. So if it's lesser than 1, the x is lesser than 1, you will see the relative distance between the nearby data points get larger. Larger means more than 0.1. So for the x variable, the step between the data point, the nearby data point is 0.1 step. But after you apply the log transformation, then the steps can increase when the x is lesser than 0, lesser than 1. For the x is greater than 1, the distance between the nearby data point actually gets squeezed, okay? So that's a characteristic. Then we're moving on to here. After we apply the log transformation, we apply it to a dependent variable, y, log of y. Then what is the impact? What is the relationship between x and y? Okay, so the relationship for beta 1 is interpreted as per unit increase in the independent variable x are associated with 100 times beta 1 percentage change in y. Also, there is an example here. If beta 1 is 0.07, the x being education, that means 1 more year of education increase the average salary by 0.07 times 100, which is 77%. Okay. Another rule that is shown here, right? So you apply both log to x and the y variable, then how you interpret, say, let's say beta 1 equal to 1.7. Again, x is education, y is the salary. Okay, it says 1% of more education increase the average salary by the beta 1 itself. So beta 1 is 1.7, so just add a percentage after that, so 1.7%. Okay, so that's important. So next you will look at this wage one data set. We'll check the skewness, then we apply the log transformation. So let's look at that. Okay, in order for you to use the wage one and the wage data set, you need to import this called Woodridge library. So you need to do this library Woodridge. If you don't have that installed in your computer, you need to install it, uncomment and install it. Okay, so I already have it, so I don't need to install it. So I just run it. Okay, then after that, let's have a look at wage one. Wage is this, and the length, how many elements? There's 526. Then we do a histogram of this wage that is seen here. It is very clear it is a right skew, right skew. So I want to check how much is the actual skewness. So we use a skewness function. So you can use this library E1071 or use another library. Yeah, this E0171 will work. This library will work. There's another called momentum library. So LIBRARY, if I'm not wrong, moments of momentum. Library may also work, but I'm not particular. I can't remember it exactly, but either momentum or moments. Okay, library. So this one, park it there. So skewness of wage showing 2. If it's greater than 1, if it's greater than 0, it's right skewed. Lesser than 0, negative value, it's left skewed. So if it's positive and it's more than 1, it's highly right skewed. So after that, we apply the log transformation. We show a histogram of applying a log transformation. We apply log transformation. After that, we show the histogram. Then we also calculate the skewness of a log transformed wage, which is still positive, but lesser than 1. So after that, what we are doing is wage is a dependent variable. It's a target. So we apply the log to the wage, while for the rest of the independent variable, we keep it in its native form. So we don't apply any log transformation. Then we run it. So this is how we interpret. So I see education, experience, tenure, and female. Okay, so next is what we are analyzing, or it's saying next slide is saying the regression shows 1 year increase in education. Okay, 1 year increase in education is associated with this beta parameter times 100, so 8.7, then with a percentage, so 8.7% increase in average hourly earning. Okay, and this p-value is very small, so it is very significant. Okay, so it's actually very small. Yeah, then for female hour earning rate are 0.30 times 130%, negative 30%. That's lower than the male on the hour rate. So this is what we're seeing. Then if we apply the log to experience, so at meantime experience is still quite significant. It's 0.05, less than 0.05. It's significant, and this is a coefficient of it. So what we are doing is we are applying the log to experience. Then we see, we'll observe that the coefficient for log experience become highly significant. So we apply the log to experience, then we run it. Okay, so now we're observing that yes, 1% of experience increase will lead to this beta 0.11, just direct percentage increase in the average hour earning. Okay, another thing you want to notice between these two models is the first model is without using any log transformation for independent variable. Your R squared and adjusted R squared is about 0.38, 0.39. Okay, by introducing the log to experience, then your R squared actually increase. So that means the model is more accurate. It can explain more variations. More variance of your target variable set, etc. So in general, prefer to have a higher adjusted R squared and R squared. Okay, so this is also what you observe. Then we'll move on to the 11.2. Okay, 11.2 linear regression. Goodness of fit. So we measure goodness fit by using a called R squared. So R squared is a it is the linear correlation coefficient between two variables, then we square it. So that's called R squared. So what is the linear correlation coefficient? We need two variables, X and Y. So here is a predicted hourly rate and your actual hourly rate. Then with these two variables, you can calculate the linear correlation coefficient. Then you square it, you will get R squared. Okay, so that's the one. Then there'll be a few explanations on what is a range of R squared. So okay, R squared can be understood as squared correlation coefficient. Okay, and the correlation coefficient is in the range of -1 to +1, right? -1 to +1, you square it, then it will be in the range of 0 to 1, 0 to 1. So higher the better. So higher the better. Then next is adjusted R squared. So adjusted R squared is introduced because when you're adding more independent variable, it always add more information. So the more you add, the higher the R squared will be. And the R squared will not reduce by introducing more independent variable. So imagine if this independent variable is completely useless, then your R squared will not reduce because the rest of the variable will at least explain to that level. So adding a useless independent variable is equivalent to adding a adding an unrelated variable. So linear regression is expected conditional expectation. So conditional expectation, you add more conditions into it. Then if the condition is actually useless, it doesn't explain anything, then you just leave it there. So R squared just R square is to try to penalize it because we don't want a model to be complicated. We don't want to introduce any meaningless things. Then they actually factor into these. If you add it, at least you should have certain degree of increase in the raw R squared. If it's lesser than that, basically you're adding a variable which does not be benefit enough above the average, then it's better not to add that. So that's adjusted R squared. So you will notice adjusted R squared will be always less or equal to the multiple R squared. It'll be always less or equal to R squared. Okay. Okay, so that's the review of the theory part. And next, so we move on to look at the tutorial question. Okay, let's look at the tutorial question. First one is the estimated regression model is log y 3.64 plus 0.5 log x, where y represent the expenditure on the food, x represent the income. Okay, then you want to interpret the slope coefficient beta 1 of 0.5. So what I will do is I'll now move on to this R tutorial solution. Okay, R tutorial solution. So I will copy everything here. I copy everything here so easier to read. Okay, for a few of the questions. So first is question one. Question one, analyze. The slope coefficient indicate that 1% increment in the income lead to a 0.5% increment in the predicted food expenditure. Because both sides you have log, right? So we have log x means 1% of increment in income. It will lead to this beta. Beta. Lead to this 0.5%. This exact value or this exact value. Okay, so let's have a look. Okay, 0.5. Yes, you're right. 0.5. Okay, such here. 0.5, 3.64, 0.64 here, it should be 0. The estimated is 3.64 plus 0.5. Next is 7.6, 0.05. Okay, right. You're right. So it should be 0.5% directly. Okay, then the second one is 1 unit of increment in X, which is income, will lead to 0.05 times 100, which is 5, then 5% of the increment in the food expenditure. Yeah, right, 5% increment in the food expenditure. So the theory that we're using here is shown here. Shown here. So look at these two. Look at these two. These two. Okay, then question two. Question discuss the reason why logarithm scale should be considered in place of linear scale in regression. Okay, so question two. The reasons why. Okay, so first the reason is logarithm scales help to normalize data, reduce skewness, especially right skewed, right? So it will reduce skewness. And to handle the call multiplicative relationship. So in many real world scenarios, the relationship between the variables are not additive, it's multiplicative. So for example, there is a scenario here. So the income X affects the sales. And the relationship is sales equal to K times the income powered B. So K and B are constant. So this is not a additive relationship. It's not a linear relationship. It's actually a non-linear relation, which involves the power. Okay, so taking the logarithm of the both sides, you will actually convert it into say log y equal to log k plus b times log x. So that's a transformation with log on both sides, right? So this form is basically y equal to a constant plus y equal to beta 0 plus beta 1 times x, another variable. Okay, so this is a classic form of a linear regression, not a linear regression model, additive model. So this is transformed to a linear ones, and yeah, that's one. And especially when you need to consider the variable x, let's say here is income. There have been other variables like educations, like work experience, and some other variables. Some other variables may be additive, but in order for multiple variables, multiple independent variables to jointly predict the dependent variable of sales, you follow a linear regression if you're using a linear regression model. So every independent variable, their relationship to the dependent variable should be additive. So you can't mix those non-additive with additive. So, but after applying the log, you basically convert those multiplicative relationship to additive relationship between income and the sales. Then you add on more independent variables, then the regression model will be still strong and workable. Okay. Okay, so that's one of the main reasons. Then how log transformation reduce skewness, that we have demonstrated that it will actually squeeze the values and stretch some other part of the value. So R squared as a good is a fit measure. So we have R squared, we have adjusted R squared. So R squared actually explains the variations in the dependent variables can explain the variations or the variance in the target variable, the dependent variable. Okay, so that's why. So for example, 0.8 means 80% of variance in the dependent variable can be explained by the combination of independent variables in the model, and leaving 20% unexplained. So another 20% can be randomness, can be error, can be some other underlying unknown variables which we have not be aware of, and we don't have the data for it to explain. So question 3 on what is R code. So let's look at the question 3. Question 3 is the package in the Woodridge Kia LMC, the data. Then this is the incinerator location impacting the house price. Okay, so that's the one. So price is beta 0 plus beta 1 times log distance to the incinerator, then plus the error term. Okay, so check the skewness of price, then consider about. Okay, so let's look at that. I've covered question 1, 2, then we're moving to question 3. Okay, effects of incinerator on house price. So first, check the skewness of price. Okay, let's check the skewness of the price. You need to import the Woodridge library, Woodridge package. So when you call library, you're actually moving the library's content into a computer RAM, and then you can use. Then the data set called KRLMC is shipped, is loaded into a memory when you are loading this library. So that's the price of it. So histogram shows it's a right skew. Okay, right skew. Then what is skewness value? Let's print it. It shows 1.13. So it's greater than 1, so highly right skew. Then after that, we can apply a logarithm to it. And then we show the histogram of the logarithm. So this is one that is log transform. Okay, so earlier it's not log transform, the raw price distribution, and this is a log price distribution. So it looks more normally distributed. Let's have a look at the log price. Also, log price is near 0. It's actually slightly left skewed, but it's around 0. So next, we're saying that asking expected sign of a coefficient for log distance. So basically, we see the distance to the incinerator. The longer the distance, in general, we want to leave a little bit far from that. The longer the distance is the house that I'm more interested. So the housing price is likely to be more expensive than those houses which is near to the incinerator. Okay, so larger the distance, higher the price. So they are moving in the same direction, so they should be positively correlated and with the same sign. Same sign. So next is estimate model and interpret the coefficient. So we have this price with log distance. So this is required from here. So price and log distance. We're only using one variable. So when we're using one independent variable to predict the dependent variable, this is called simple linear regression. Simple linear regression. So if you have more than one variables, more than one independent variables to predict one dependent variable, this is called multiple linear regressions, basically multiple variables linear regression. So now we have a look at this summary, okay? So this model shows that intercept this amount of money, and this is the log distance, this is the coefficient beta, okay? So price is a default price intercept plus the distance to this incinerator. So interpret, okay, both side has log or only one side has log. Yeah, one side has log. So 1% increase in distance from incinerator, 1% distance increase is associated with about $23,000 increase in the price. Okay, so increase in the price. Then include additional independent variables, so which is the A1, 2, 3, 4. Here, estimating and interpret the coefficient beta 1. So add the following independent variable there. So log area, log land, rooms where the square foot of the house land is a lot size, and so on. Okay, so now look at the effect of incinerator. Okay, so we have a model B price regressed by a few more variables. Okay, let's run it. So now after running it, what you are noticing here is first log distance, the beta parameter for log distance become insignificant. So this one p-value is not significant. So that means the distance might not be relatively that important compared with other variables. What other variables are more important? We're looking at the area and the land is quite important. Actually, the area is more important because the beta value is very large. Okay. Yeah, the rooms not so important because the p-value also small. So this is what we are seeing here is interpret after adding additional variable, the effect of the distance become not significant compared with area land. Okay, right? Yeah, you can also compare these after that based on adjusted above 2 matter which one is better. Okay, so let's have a look at adjust R square. Actually, you can look at the data from here. So earlier, using only the incinerator as a independent variable, we have adjusted R square of 0.065, which actually this is a very small value, 0.065. So after we introduce a few of other variables, the R square has increased to 0.4. 0.4 is quite okay and much better than 0.06. Yeah, so basically it's increased. Now we can bring it. So the adjusted R square, which reflect the fit of this model. So model 3B should be selected due to high adjusted R square. Okay, so although 0.43 is much higher than 0.06, both of the model cannot be used in the production in the real world. It's because the independent variable only explains about 40% of variations, another 50–60% of the variation, why the price is this high, why the price is this low. Variation in the price is not explainable. It's not explained. So that means there are some more important variables which is unknown to us at the moment. that can potentially explain the variation in the price, why some price is higher and lower, even with the distance, area, land, rooms are all the same. Let's say 3 rooms and landed in CBD, then the area is 1,000 square feet. The distance to incinerator is the same. So everything is the same. You will still find out of these conditions, there may be 100 houses. The 100 houses, some are more expensive, some are a lot less cheaper. So the variance is very large. Because earlier we will expect if the house have the same values for those variables, they should be selling at a similar price or the same price ideally. But in fact, what we observe in the market is the price range is very large. So that means there at least there will be some other reasons which causing the house, these house, some are more expensive, some are less expensive. There are cities. The variation in among these 100 house, at least 60% of the variance cannot be explained by the known variables. So this is how you interpret this R square, okay? Okay, next is use the data set Apple from the package Woodridge. We plan to estimate the following model. Okay, so this is the eco pound. So the pound of ecologically friendly apples, labeled apples, that family would demand, and the eco price is the price of the eco labeled apple, and the reg price is the regular apple price. And first check the skewness of eco weight. There is log transforming form. Okay, let's look at these ecologically friendly apples. So check the skewness of ecolog. So check the skewness. Oh, highly one. It's extremely high skewed. Extremely highly skewed. So what does this mean? So very few customers actually buy a lot eco-friendly apples. Very, very few. The majority is buy very less or even not buying it. Okay, so we do a lot of transformation. Yeah, we'll do a log transformation. Why not? Let's display the histogram again. Do a log. You are seeing this, so yeah, it looks much more normally distributed, but you are seeing a lot of infinite, negative infinite, because it's zero. There are a lot of zero in the a lot of zero. So a lot of zero. Basically, some customers they actually never buy or don't buy it. So log zero is negative infinite, which does not exist. So if you say that you want to run this model, then you run it, they will say there's an infinite. You will see some errors. So it can't work in this linear regression model. So this is the problem with log transformation with zero values. So a few ways to navigate this issue is first proceed without log transformation or exclude the zero values. This is not recommended, so not to exclude, because getting the sample size small, sometimes the sample size is to match with other sample size, they need to be in the system, so you can't easily exclude them. So the numbers before the log transformation into the variable itself. So we actually change from 0 to 0.01. So it's a very small number. Okay, so first thing we try is we proceed without log transformation. So we use the purchase the pound, regress with regular price and the equal price. So we have a summary of it. Let's have a look. So what I see here is first I look at adjust R squared, it's 0.03. It's a very small number. And that means the purchasing behavior, the customer who buy these pound, this amount of eco-friendly apples are not really explained by the price. Okay, it's actually not being explained. Only 3% is being explained. But the beta coefficient of regular price and equal price of the apple are both significant. So this is what the statistic tells you. They are very significant, but it just these two variables explain very less. So this is very similar to the incinerator. Incinerator in the radar example. Without knowing anything, the distance to the incinerator actually impact the house price, but they explain only a very small variation. It actually influenced the house price very limitedly. After that, we are adding area, square feet, number of rooms. They will find that explain much more. So same thing here. So the amount of eco-friendly apple being purchased by the customer are not really impacted by these two variables. So that's why you are seeing that adjusted R square is so small. So there must be some other variables which can help more in explaining why customer buy and the apple do a log transformation. So add a small number to avoid the problem of having negative infinite. Then after that, we say, okay, we do a log equal log plus 0.001. Basically, we add a very small number. Then we replace. Then we run this model. So this time, what you are seeing here is, again, both of them are significant. The parameter -8 and the 7 are important. Okay. Yeah. They're important. Yeah, okay. Then you see that just R square actually increased from 3% to 8%. So slightly better, slightly better. Okay, so question 5. Okay, that's the one. Statistically important, report the p-values. Okay, yeah, they are statistically important. The p-value are very small, very, very small, highly significant. But this kind of model, regression model, say if we want to use it to for the future predictions based on the price of these regular and eco-friendly apples to predict how much customer is going to purchase, this model will be not reliable at all because it only explains 8%, 9% of this variance. That's basically it's very far from the accurate prediction. You would expect to see this one near 99%, 98%, or at least above 95%. Then overall, in the real world, then we may consider to use and deploy it. Okay, so question 5. Question 5. One important decision regarding what additional independent variable, blah, 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 independent variable, education's wage. Okay, so we're looking at this wage data set, looking at education experience, tenure, and male, female to predict the wage. Okay, so this is what we're doing. The purpose of this one most important. Okay, that's a very long one. We'll read through it. So we have a few things to do. Find the deviant key interest of the group, populate the list of necessary independent variables. Okay, I'll see this is the last question. Okay, cool. So I think first thing is let's look at the wage 2 data set. So this is a data set of wage 2, data set wage 2. Building a model, actually we can wage 2 data set. This is data wage 2. Okay, get it. So where is it? Where is it? Let me do this. Let me clear everything here. And let me run it. Okay, so I have this wage 2. So I have a look at this wage 2. 935 observations in the wage, 17 variables. Okay, 17 variables. So wage, so this is a wage, IQ, blah, blah, education, experience, tenure, age, married or not, ethnic groups, father's education, mother's education, blah, blah, blah. Okay, so let's look. So the first thing is we do a regression model, okay? Regression, just a normal regression, multiple linear regressions, and we interpret it. So what I seeing is education experience and tenure is shown here, or are very significant. Okay, then, but I just say arc square is pretty small. Again, small, 14%. Okay, so the education is 74. So basically, with 1 year of more education, your hourly wage is $74 more. So the second one is saying, okay, well, actually introduce a few more variables, father's education, mother's education. Okay, then run it. So what we are observing here is father's education. Yes, it's significant. Mother's education isn't super significant. Anyway, significant. The appearance is also important. Then the education of the person itself gets slightly reduced. Okay, so you're introducing a few more variables. And what do you observe? One thing very important is to observe whether the adjusted R square increase or not by introducing more variables. Then this is the way to tell you that adding more variable, independent variable, whether it can help to explain more variance, whether it can help your model to be predict more accurately. Okay. So I just say R square increase from 0.14 to 0.15. So basically adding two variable, father's education, mother's education overall is useful. Okay. Then after that, we're looking at the coefficient of which one is significant. Okay. So the education for that person is important, experience, tenure, and so on. They are all important. So this is being explained here. So increased, then the education actually decreased. When you're looking at the decrease or increase, you also need to look at the intercept. So because the intercept actually also changed, so it will impact all the coefficient of the variables. Okay, so your intercept gets slightly lower. So yeah, then your education actually reduced. So whether you look at it, the father's education increased to contribute into the hourly wage of that person, that person's father's education somehow. The model tells us, yes, it's important, it's correlated, and it's significant. So what it's saying is, 1 year of your father's education will help that person, the son, to earn $13 more per hour. So while mothers will have less impact. Nevertheless, the mother's education doesn't seem to be very significant, influencing the the child's wage. Okay, even if it is significant, the beta value, the coefficient is small. It's smaller than the father's education. So the father's education seems to be more important average person's wage, hourly wage. Okay, so that's the one. Okay, so that's all for today for this log transform the linear regression. Yeah, thank you. Bye bye.